What's going on, everyone? Embedded Monkey here. Today is Embedded Adventure Day 21. And by the way, I ran out of coffee. Yeah. So I'm back with the Embedded Adventure Day 21, where I'm as a complete beginner trying to learn different stuff about embedded, about freertos, about different ADC, DAC, about Wi-Fi communication. There are plenty of series now. So yeah, in previous series, we actually fixed the bug with the freertos task creation, and well, the bug was actually pretty interesting. Um, I can remind you guys a little bit about what was in previous series. Yeah, so we just created a basic task, and I tried to just simply print the name that I put as a param. Yeah, and I tried to like change like the first element of this array to actually see what will happen. So that was kind of like a data race experiment. Well, not like the data race. We wrote it here and output it here. So pretty much that's okay. But today we're gonna do some more experiments on data races. That will be cool, I guess. Yeah, and oh yeah, and by the way, check out the new cap. Just bought a new cap, guys. Think that will be pretty cool, I guess. Yeah, maybe better than the old one. Okay, so let's go. Um, yeah, and of course I use our mastermind ChatGPT for different stuff. But okay, so um, let's create several tasks. Yep, like no, I want to I want to just currently check the plan because I had the plan that ChatGPT gave me on FreeRTOS, so we can actually check this out. That was a long time ago, but we can just stick to it. So yeah, we basically created the tasks. We understood how to actually work with them. The stack size is not very clear for me because like there was a problem actually with the stack size in previous series. So the stack size is actually goes in bytes, if I'm not mistaken. Um, let me just check. One moment. If I'm not mistaken, it really goes in bytes. Stack depth, the size of the stack finance, number of bytes. Yeah, and the ChatGPT said it number of words, but actually no. And the absolute minimum is just like 1024 bytes or 256 words on esp32, because on esp32 the byte is, or the word is actually 32-bit. Yep, not 16-bit. That was a little bit of a mistake, but okay. By the way, I would like to actually cover these things here, and then I'll probably do the data race thing. Yep, so first of all, let's clarify a little bit about stack size, because I would actually like to know a little bit more what is stored there. What is usually stored on stack in task? Understanding it will prevent 80% of mysterious crashes. Very intriguing, yeah. Short answer first, then we'll go deep. Task stack holds everything needed for that task to execute and resume correctly. Are you serious? Whoa, that's incredible. What a discovery. Holds everything needed for a task to execute and resume correctly. Wow, I didn't know. So, what's in particular? Like, yeah, um, during context, we just program counter, stack pointer, CPU registers, status registers, function call frames, yep. Okay. Local variables, yep, of course. But in this task, I haven't actually used any on-stack variables or, well, actually, these ones are function calls. So if we call a function, it should be put on the stack to have a return address and to know where to continue. Yep. So basically, yeah. So at least I have to allocate, no, like at least I have to specify the stack size that is enough for 2 function calls. All right. So probably there was a mistake. Library call usage, hidden danger calling. These have deep call trees. Well, probably, yep. But actually, the size of 256 words was enough, as we saw, so probably okay. That's interesting, because, prior to compilation, you don't really know how much each of these calls will take. So you will actually end up with some guru meditation error when the program crashes on the esp32. So you will just have to do some experiments. Okay. Right. So understandable. Well, no. Actually, I have a question. Well, if so much things can be stored on stack, how to specify optimal size prior to compilation when we don't know how much space will every call or we can predict how much space will variable take, but not how much like every call take. Yep. That's like a genuine question. There is no single magic number. I'm not trying to predict it perfectly. Let me answer this in practical engineer grade way. Iterate. Simple logic. Uses logic. Network JSON. So basically we just experiment. We just do a bunch of experiments, iterating, and that's all. It's like the analogy, I guess, the elbow method, if you are familiar with machine learning. This is a completely different field, but there was like an elbow method when we know like we're trying to get the optimal number of some hyperparameter for, I don't know, some clusterization method, and then we see how the loss function like falls. That's like not not directly related to embedded systems, absolutely not, but that's a similar idea, I guess. We can actually implement it here. But okay, so that's clear, right? So what else? Just to verify, task states. Yep, task states. I saw like the One moment, free RTOS task states. Yeah, those states. I just want to actually understand it. This picture completely, so I'm just gonna put it to the mastermind. Yep. Can you? No, I guess that's not the best quality. Probably I should stick to another one. One moment. Even worse. Why are they so? Well, probably that is okay. Okay. Can you explain the states of the state machine of a task, of a freertos task? That yeah. Okay. Running. Okay. The 4 core task states. Sorry, guys. Suspended, ready, running, blocked. There are no hidden states. Okay, meaning the task is able. So ready state is the task is able to run but is not currently running. Has all required resources, not waiting for time or events, waiting only for CPU time. What puts a task into ready? Task creation, event unblocks it. The task resume. Okay. Delay timeout expired. Hybrid task stops running. Ready does not mean executing. Okay, so it is just waiting for a free option to occupy a core, like a CPU core, to work a bit. And well, it works until some of the high priority tasks leave the core and free up the space, I guess. Okay, running. The task currently owns the CPU. Exactly 1 task per core can be running. esp32 dual core up to 2 running tasks. That's actually very limiting, by the way, because there are a bunch of system tasks that have to be running on the ESP, and if you have more than 2 like application tasks, then probably it's a little bit limiting. But okay, it's like microcontroller, so it's better to manage all of these very precisely to not run out of resources. Yep. Scheduler decided who runs, how task enters running. Okay. Selects it from ready list. Okay. So these are pretty clear. Blocked. The task is waiting for something to happen. Alright. Time delay. Queue. Okay. Semaphore. Take. So we actually had this state here. We have the vtask delay. So basically, here the task running, like right after this function, it's probably in ready state because we have to do some work here. Here it is in running state, and here it is blocked state, basically. Yep. And spin the task is forcibly stopped regardless of events or time. State transitions ready to running. Well, okay, if I understand it, the state, okay. So, if ready to running, then the scheduler decided that this task can be executed on the core. Okay, if we transition from ready to suspended, then vtask suspend, okay. Running, okay. So I guess the suspended is basically vtask suspend or vtask delete when we completely deallocate this task, and we'll say like this, it can't be really running any further in our program. Okay, so this is like the dead state, I guess. Ready, okay. Not the dead, but the like the pause state. The dead state is when it deleted, probably. So these state machines basically only works if the task is not deleted. If resources are allocated, they stay there, and we just said that currently we don't want it to execute anytime, and well, yeah, we just don't free up resources. We just leave them there, but probably we should actually delete them in the end. Okay, so we can resume. We can block and unblock by events. Yep. All right. By the way, cool picture. I'll probably put it. I don't know. Actually, this is a plan that I'm writing here for this embedded adventure, but I don't know, that's a pretty cool diagram actually. By the way, I thought to actually put the notes that I'm unfortunately not making to the to some Notion or to UNote to it's just more convenient than to write them by hand. Probably I should consider this optional. By the way, let me know in the comments what do you think. Should I actually do such kind of maybe explanations of some topics, something like that? Okay. So more or less, I'm clear with these topics. Let's go to the data arrays. Yep. Let's create the second task. I'll call it. Well, monkey task 2 is too obvious. Let's call it donkey task. Who knows? He knows. Okay. It will do absolutely the same thing. And we're just gonna create it with the same stack size, with the same parameters, absolutely the same thing. Tasks was successfully created. Yep. And we are putting here the params. Yep. Now I want to, well, okay, let's just simply print it. Yep, let's simply print it. Just see what happens, okay? And then I'll probably try to modify them inside both of tasks just to see what happens. Probably nothing good, but interesting. Connecting that tiny little thing. Yep. Trying to flash this code. Okay. I hope no errors will occur this time, of course. The program is too simple. Yep. By the way, guys, yesterday there wasn't a video because, again, I've had a very important subject to, kind of exam to pass in my university, so unfortunately I wasn't able to record that thing, but yeah, we're doing it today. That's actually amazing that I'm still doing it. Okay, so as we can see, it ended up in a little loop. So it seems like it's not, probably both of these tasks occupied the, they occupied the 2 cores, and this function is not able to continue its work. Yeah, as you can see, there's, well, maybe I'm mistaken, it's actually printing, it's actually resetting endlessly. Well, that's probably not cool. For some reason it resets completely every time. Well, but I'm currently not pressed, well, I can't press the button, actually. Well, let's just leave, if we can, of course. No, probably can't leave. No, can't leave. Yeah, finally. So, I don't know, for some reason, well, I'm not currently pressing any reset button, it just resets automatically, for some reason. Well, I can reset it actually, it's multiple times. But for some reason it resets. So it gets some signal TG1 WDT is reset. I'm just gonna Google it. Yep. Quick bot. Oh, I guess I know, guys. Yep. I'm a little bit hacky. Okay. So, yeah, they're getting the same error. Does the boot get a specific type of event that transpired and it caused the reboot? Same issue. Log. Moving on from using Mongoose OS and using esp32 later. Leave the system and over. No, that's some too much context. Understanding watchdog RST0. Well, yeah, that's the exact error. I read the watchdog documentation, but not much makes sense. Does TG1 task group 1 refer to the tasks bound to CPU 1? Oh, so TG1 is actually a task group. Okay. Okay, so TG1 watchdog timer system reset. One moment. What is a task group? Task group. Because interesting, I haven't actually created any group. Oh yeah, guys, yeah. Of course. Of course. Of course. Okay. So yeah, what is a task group? Because currently I'm not really, I'm a little bit confused, like, what is a task group? such thing as task group object. When people say task group, they usually mean one of three different things. The close real comes to event groups. Task group actually means an event group. What an event group is a set of bit flags used to synchronize multiple tasks. Okay, why people call it a task group? Many tasks can wait on the same event group. Okay. Events affect a group of tasks. Tasks can be released together. Logical task grouping. Well, it seemed like I'm getting some error with the tg1 dolly dt. Okay. As far as I understand, it is related to task group 1. Sorry. Oh, it's timer group. This guy says task group. Could be the wrong here, but oh gosh. Why it is so hard to understand these esp32 errors? Oh shit. And they actually timer group watchdog error, which would be an interrupt watchdog. The interrupt watchdog is able to invoke its pending handler for some reason, and you're getting system reset. Oh, so again, I guess the problem is that we occupy all two cores. We occupy all two cores, and probably that's why we actually can't really actually allow the system tasks to work. Maybe I should change the block period here. I just have a little bit of guess. So when we just created them, we've done some work, we blocked, and they probably occupied like 2 of the cores, as we can see. So they executed together, yep. Then they completely unblock, and then they block again simultaneously. Probably we can't do that, so we have to increase one of their block time for more couple of seconds. Let's try. Why not? I guess. Well, the result will be actually interesting because they shouldn't now work together like spamming that print every time. They should actually do it asynchronously a little bit. So first of all, so this will be printing with 2 times higher frequency than this one, which is obvious actually. No. Actually, no. Let's see, is there the same? Yeah, error is the same. Okay. Right. In this, start scheduling the together. Timers. Okay, let's now stick to this answer. I hope this will help us to get a little bit more of understanding why this happens. Okay, so Yeah, we have two timer groups. We already know, guys. We already know that's from, I don't know, actually, probably from this series, from day 12. Yeah. Um, two timer groups, two configurable timers. And yeah, and we also have like a watchdog timer in every of the group. Yep. Why the watchdog exists? The watchdog resets the system if the CPU gets stuck, tasks don't yield, interrupts run too long, scheduler stops running, all that stuff. How this relates to freertos task, even though it's hardware, RTOS behavior can trigger it. Task never blocks or yields. Long blocking inside critical section. Well, we actually have a block state here. Yep, block state here. So everything should work, probably. Everything should work. Yep. Or maybe because we never did. Oh. Whoa. One moment. We actually use the same task handle. Probably we should actually use different. Let's call it M task handle, and we also will have the D task handle, and the M task handle goes to the monkey task, and the D task handle goes to the donkey task handle. Okay, right. And if M task handle, then we delete the M task handle. Well, this like a serious error, because we're just losing the ability to actually delete the task afterwards. So we definitely should actually do that. Let's just compile it again. And just we'll continue reading. Infinite loop, not main without delay. No. I saw running too long. No, that was a long time ago. 8 series priorly. Yep. No, the same thing. Getting the same thing. Ensure every task calls vtask delay or xq receive. Well, of course. We learned that basic stuff, so everything should probably block correctly. So we use vtask delay. Even here we use vtask delay. Yep. Okay. Never busy loop. Keep ISR short, avoid long critical sections. Debugging tip very useful. Fig watchdog. Task watchdog info. The watchdog. By the way, component config. By the way, that seems quite useful. So, you mean that we can actually see which task just completely blocks the CPU config. Yeah, we go into that fancy menu. A very fancy menu. Well, oh, I just misclicked a little bit. Yep. Okay, let's go to the component config to what? To ESP system settings. To watchdog timer. By the way, we can actually change the CPU frequency. We actually can change the CPU frequency. What the hell? Memory. Yo. That's interesting. By the way, task watchdog timeout period. We can simply change the watchdog timeout period. So when the task will, so it goes up to 60 seconds. So if we assume that if task completely blocks CPU for 60 seconds, it is unsafe. So this is basically the definition of unsafe. Okay. Oh no. Watch CPU, 0 idle task. Enable task, watchdog okay. Enable task, watchdog timer. By the way, we can actually disable it. We can probably actually disable. Yo, here we also have an interrupt watchdog timeout. But we're actually not really interested in interrupts now. So probably that does not make sense. Let's disable it. Let's really disable it. I don't know. Just for fun. Just for fun. Yep. Let's disable that thing. And quit. I'm just gonna verify that everything's saved. Because I'm not really, I'm not a frequent user of this menu config. I just want to verify that everything is okay. Okay, component config system, where it was ESP system settings. Yep, everything is okay. And now let's compile it without any watchdog time. I know it's probably unsafe option, but we currently have 2 tasks running, so nothing serious should actually happen. I actually hope that nothing serious will happen. Oh yeah, so it will actually do now a bunch of stuff to load the configuration there. Because as far as I know, it also flushes. By the way, another interesting question. How the config settings from idf.py menu config got flashed to the esp32. And then connect build system freertos config. Does not flash settings directly, generates configuration files that are a firmware binary. Same system as Linux. Okay. That will take forever. So let's just chill and read a little bit. Freertos hurts. Okay. Reach your code. Compile time injection when you build. It's included automatically. Oh, so basically they are all in SDK config. So probably we can actually find this SDK config. Well, not here, it's still compiling. Maybe in some, yeah, here, SDK config. So basically, this is just a long file with different definitions of some settings that are basically included to, well, implicitly, or no, actually explicitly, here, SDK config. And in MonkeyRTOS, I guess we have the same thing. We have the same, actually no, we do not include the SDK config here. We actually do not include it. Huh. I think we actually should include it. Since we want to use all these new configurations. So that's why it's probably not working properly now. Guru meditation error. No. We should it won't stop. We get the Guru meditation error. And by the way, really, isn't there a problem with including the SDK configuration? Because I guess, well, we actually should include it. Let's just... Sorry. Yeah, let's try including it. That's actually strange that we use the... That's actually strange that Guru meditation error occurs since we fixed it in the previous series. But okay, we'll just see how it works. No, actually the same shit. Again, please stop. I'm just spamming it. To stop it. Okay, so probably... Yo, what are... These are some meta addresses with all Fs. That is something not normal, I guess. Well, okay, what if we don't disable it completely, but we try to increase the time when the watchdog timer actually starts to panic and resetting the CPU. Yep, so let's just make a little bit more easy condition. So when we enable it, what we can modify: initialize task watchdog timer on startup. Yep. Invoke panic handler on task watchdog timeout. Panic handler. By the way, let's enable it, because probably it can give us some information about the task that we're running. Seconds. Yep, let's go. Let's just save these options. Rebuild it again. maybe if it will output the panic message, we will be able to locate where the problem is. Because, like, you know, it's just blowing up the report with different addresses, so we can actually see. Well, we can actually probably see the code files that are and the lines in them which are responsible for triggering the watchdog timer, possibly. Yeah, it can be a random, because you know, multi-threading is not the safest thing. We probably, when we blocking that thing, we have a choice. Scheduler have a choice. Yep. So let's look like again at the state machine. So the scheduler have a choice which task to put from the state ready to state running. Monkey task or donkey task. They have absolutely the same priority. They have absolutely the same stack size. The same params. Only different handlers and different names. So that's quite interesting. Maybe it will just take the tasks that was created firstly. Yep. Probably it will stick to this way. Okay, we'll see. Just will wait a little bit. Yeah. Flushing. Okay. Is there any more information there? Actually, no, we don't get any panic information here. Or no, or we get panic handler at here. Start this. Okay, guys, I'm gonna do one more attempt, and then I'll just completely will ask the mastermind what's wrong in my code. Yep. You know, guys, I like doing experiments. Well, probably if you watch me, you can see that I better spend 3 series on fixing bug on my own than to just immediately drop into ChatGPT. Well, we don't have any information here, right? So it's actually, we can see that it calls some panic handler. Yep. But I can't really see any more information about the program that like this. Sorry. Oh my gosh. I can't see the information that can be useful for like locating which task trigger it or no. And by the way, it's always calling the monkey first and not the donkey. Pretty cool, pretty cool. So I was right. I was right. Alright. So, again, let's try to increase the time of watchdog timer. So that will be the last thing that I will attempt to do. And then we'll ask the mastermind to actually fix that thing. Yep. System settings. Okay, so it tells us it's like 5 seconds. I guess it's not the case actually, because if you can see, you probably could have seen it. It actually resets much quicker. Not even like 2 seconds. So there's like no place for 5 seconds here. maybe we should increase both timeouts here. That would be cool. And also let's check, are there any useful options in watchdog timer besides like the time of watchdog timer? What is watch CPU zero idle task? It's like react on certain core, I guess. CPU. Yep, let's take a snapshot. Okay, just gonna ask again. I'm a little bit too addicted to ChatGPT. I guess this is a bad thing. Okay. Can you explain these menu config options for watchdog timer? Different from hardware touch. Never yield long critical deadlocks. By the way, it is a good way to defeat deadlock. So, if you guys don't know, like the task deadlock or thread, thread deadlock is when they block each other, as far as I know. Yep. Yeah, so this one wants this object, this one wants this object, and they are like blocking them. So they blocked each other and they can't really do anything without it. So the watchdog timer basically waits for 5 seconds and destroy them both. Pretty ruthless, but yeah, that solves the problem. Task watchdog timer on startup. Okay. TWDT during system startup. Task register early. Okay. Task can go without building. Well, actually, We actually correctly block the task once every time every 5 seconds. So as you can see, well, 4 seconds of course, but well, no, there should be not like the block time, but the block should occur for once in a while. So once in the 5 seconds or once in up to 60 seconds, right? So this call takes not even a second, it takes like several milliseconds, so probably we actually done everything right, so I'm just too sleepy today. Hey guys, no, sleep is very important for your health, for your mind, for your brain. So sleep well. And I'm gonna use this mind to just tell me what am I doing wrong, like with this watchdog timer. Can you say what's wrong in my code? Because I, well, correctly allow tasks to be blocked for several seconds and don't have infinite blocking loops. I currently don't understand. Maybe because I'm too sleepy, maybe because there is something I really don't get here. Your mental model is mostly correct. You don't have an obvious busy loop. However, there are several real problems in this code, and one of them is esp32, esp32. I'll go through them. Is a task and yours returns. Wait a second. Wait a second. Wait a second. Hell no. Wait a second. I'm gonna find it. I'm gonna find this moment. It was, I guess it was like in this series, yeah, in day 19. So I'm gonna find it. Oh, where? Here. Yep. I caught it. I finally caught it. Here we go. Why app main does not need an infinite loop? Why is this okay? Because app main is not the task. The main task calls app main. After app main returns, the main task deletes itself. Everything's okay. Contrast with user created tasks. Returning from a user task, not okay. Returning from app main, okay. I'm not considering it a mastermind ever again. Hell no. It's just runs me crazy. Just runs me crazy. Damn, I just want Tsingtao beer after this. Leaves the stack is in an undefined state. No, it's not. It actually works. Fuck you, ChatGPT. Fuck you. Just hate that thing. Give them at least priority 1. Well, that's actually makes sense. That's actually makes sense because here we have the yep, we have a watchdog timer for idle tasks. For the low priority tasks. We have a low priority tasks. So probably if we really increase the priority here, it can actually solve the problem. It can actually do something. But that thing run me crazy. Like, it really said the opposite thing, and okay. We actually checked that in the previous series. Everything works even if I'm not deleting the tasks inside itself. So I don't really need to delete it inside the app main. Well, guys, that's hilarious. That's hilarious. Okay, let's just do the last attempt. And I'll probably go and have some sleep, guys. By the way, guys, do you think I should make a stream? Like to do this in live, yep, and read maybe your comments in chat. I don't know. Let me know in the comments maybe. Like, would you like me to go live on this channel? Well, from time to time, of course, but I guess that would be cool. You know, I even have an idea, maybe making a project on a stream. That would be cool. By the way, we fixed the bug. Let's reset that thing. Whoa, 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 whoa. Just almost broke pins here. Not very good. I still use isolation for some reason, but just accurately put it. Just reset it. And by the way, as you can see, we never get donkey task first. We always get monkey name. Yeah, monkey name embedded, then donkey name embedded. I was fixing it for 1 hour and 3 minutes. Perfect. That's perfect. And you know why? You know why? Because when we created that task, we actually... It can actually execute on the second core. Yep, because it's not idle, yep. We can actually throw it in the second core if there is no idle task there. Then we create the second one, then it can work. But it works only here, like so. Okay. Perfect. Perfect. Okay. I would of course like to do some data race experiments, guys, but I'm currently too sleepy for it. I'm too tired. Well, in fact, I'm grateful for learning some stuff about watchdog timers. That was actually cool because this is a very frequent error in esp32. I've seen it a lot of times. like in previous series, like almost in every series where I'm fixing bugs. I don't know, here or here. I don't really remember in which series I've already caught this bug, but this is a very actually frequent error, so probably it was cool to learn about like what is watchdog timer, what watchdog timer really is. Yeah. Okay, so thanks for watching, guys. The next series, I guess, we're gonna continue just from this place. Just continue these experiments with data arrays, because today, well, we're fighting that bug. Okay, so we're gonna continue from that place. Yeah, and do some data arrays experiments, data arrays conditions, all that stuff. Yep, so thanks for watching. If you like this video, hit the like, subscribe, leave a comment. Yeah, so see you, I hope, tomorrow, but if not tomorrow, then I will just record it in the evening. So just to stay consistent. Yep, so stay consistent, guys. Learn embedded systems. Bye.